Hi, it's Dr. Chrysostimo, and this is Chapter 6, Normal Distribution. I apologize for my voice. I'm battling a cold here, so please bear with me. So here are the objectives for this chapter. We'll be talking about the normal distribution. In Chapter 5, we mentioned that Chapter 5 would be about discrete variables, whereas Chapter 6 would be about continuous variables. So this should be a little bit of a review from Chapter 1. A continuous variable is a variable that can assume any value on a continuum. So we can't really count it. It's more of a measurement. So here are some examples of continuous variables. Thickness of an item, if you measure it in millimeters. Time required to complete a task. Temperature of a solution. Height in inches. They're not really whole numbers here. So it becomes a continuous variable. These can potentially take on any value depending on the ability to precisely and accurately measure. So again, if you're measuring milliseconds or millimeters, these kinds of variables can take on any value here. This should be a little bit of a review too. So the normal distribution is bell-shaped, it's symmetrical, and its mean, the median, and the mode are all the same. The mean is denoted by this mu, and the standard deviation is denoted by this sigma here. The normal distribution also has an infinite theoretical range, so from positive to infinity to negative infinity. Here's the formula for the normal probability density function. Again, this formula I don't expect you to memorize or use, but for your information, it is here. As I mentioned earlier, we have the parameters of mu and sigma to denote the mean and the standard deviation. And if we have different means and standard deviations, it can change the look of our distribution. So A and B, which would be the yellow and the blue line here, they have the same mean, right? And remember that mean's right down the middle, but they have different standard deviations. So we have a different spread here. B and C, so B is that blue line, and then C is the pink line. These have different means, right? They're not on top of each other anymore, and they have different standard deviations, so our spread is different. By changing mu, that shifts the distribution to the left or the right. So if my mean is a lot higher, I would shift this entire distribution to the right. And if my mean was lower, I'd shift this entire distribution to the left. And then if you change sigma, that's going to decrease this spread or increase it. So if my sigma is a lot higher, my slope is going to look a lot flatter here. And then if it's a lot smaller, then it'll be a little bit pointier. We can take any normal distribution with a mean and a standard deviation, and we can transform that into a standardized normal distribution or a z distribution. And what that will do is that will give us a distribution with a mean of 0 and a standard deviation of 1. And by transforming it into a standardized normal distribution, we can easily compare different distributions to another distribution if it is standardized. So to translate a score to the standardized normal or the z distribution, you just want to subtract the mean of x and divide by its standard deviation. For example, let's say you have an IQ score of 115 with an IQ has a mean of 100 with a standard deviation of 15. So you would take 115 minus 100 divided by 15, and you would get a z of 1. So the z distribution always has a mean of 0 and a standard deviation of 1. And with the z of 1, we know that you have scored 1 standard deviation above the mean. Here's the formula for the standardized normal probability density function. Again, I don't need you to memorize this, but here it is. As I stated before, the z distribution, or the standardized normal distribution, your mean is 0 and your standard deviation is 1. And what that gives us is if you have a positive z value, then you know that it is above the mean, and if it is a negative z value, then you'll know it's below the mean. Here's an example. If x is distributed normally with a mean of $100 and a standard deviation of $50, the z value for a value of 200 is, so we would use that formula, z is equal to x minus mu over sigma. So 200, that's our x here, minus the mean, which was 100, divided by 50 is equal to 2. So what this means is that our $200 is 2 standard deviations above the mean of $100. So when we are transforming x into z or z into x even, it is important to note that the distribution, or the shape of the distribution, doesn't change at all. All we're doing is just scaling it to a different unit. So here we have the original units, $100 for the mean, and then when we transform it into a z distribution, we have a mean of 0. And we had a little bit of an introduction to finding probabilities of a normal distribution, I believe in chapter 3. So this should kind of be a review. But we can measure probability by looking at the area under the curve. So if the total area under the curve is 1 or 100%, and we also know that the distribution is symmetrical, we can also say that 50% is above the mean, or half is above the mean, and 50% is below the mean. Now we can use the cumulative standardized normal table in the textbook. It's located on appendix table E2, but you can also find it online. And that really gives a probability less than a desired value of z. So, for example, if I want to know what's the probability that you might see someone score an IQ less than 130, or less than a standard deviation of 2, then we would look this up in the table, and it would give us this probability here. So this area under the curve, here's a z value of 2. And what's this probability? That's 97 or 97.72%. So as I mentioned earlier, why you'd want to standardize a distribution is so we can make some of these assumptions. So if you have a z-score for the IQ test of 2, or if you have an ACT score with a z-score of 2, or you have a height with a z-score of 2, it's all going to be the same probabilities if we standardize it to a z distribution. And this is just how to use that table. So if you have a z-score of 2, you would use this part as the first decimal point, and then the row would be the second decimal point. So we would be 2 and 0 because we have a z-score of 2.0, and we get a probability of 0.9772. Again, this value gives a probability from z being negative infinity up to 2. So what's the probability of z being less than 2? Well, it's 97.72%. So basically, if you want to find normal probabilities, what you want to do is you want to make sure that you're translating your x values into z values first, and then you use your standardized normal table to find those probabilities. So here's an example. Let x represent the time it takes in seconds to download an image file from the internet. So see, this is a continuous variable, so we are going to want to use a normal distribution. Suppose x is normal with a mean of 18 seconds and a standard deviation of 5 seconds. Find the probability that x is less than 18.6 seconds. So we can draw our normal distribution. There's our mean of 18, and we want to find the probability that the download time for an image is less than 18.6 seconds. So our first step would be to translate our x score into a z score. So we would use this formula, z is equal to x minus the mean over the standard deviation. There we have 18.6, that's what we're interested in, minus the mean of 18 divided by 5, which is our standard deviation, and we get 0.12. So here we just transformed these units into a z distribution where our mean is 0 and our standard deviation is 1. And now we want to find the z, the probability of z being less than 0.12. So we use that standardized normal probability table. This is just a portion of it. And our z that we found previously was 0.12. Here's our first decimal point, which is 0.1. And then across the top is 0.02. And so here it is, probability is 0.5478. So the probability of getting a z-score less than 0.12 is 0.5478.